Hello everyone, my name is Mónica Simões. I am a Portuguese chemical engineer that now lives in Austria, where I'm doing my PhD as part of the International FibreNet project. This project is a consortium of 15 European academic and industrial organizations operating in the field of fibers. Our common goal is finding comprehensive solutions to improve and tailor the properties of fiber products. My host institution is the Graz University of Technology, more precisely the Institute of Bioproducts and Paper Technology, that combines practical needs of industrial partners with high-level research related with bio-based products. So, now that you already know about me, my project and university, it's time to talk about my PhD. What I do after all. Well, the focus of my work is adhesion force, specifically between surfaces and fibers. But why? What is the importance of adhesion? Actually, it's everywhere. You can observe adhesion in nature, between surfaces, fibers, and even cells. And it's extremely relevant for industry. The problem is, it's actually very difficult to measure adhesion because it occurs at the nanoscale, and how to properly measure nanoscale contact, and how to relate it with adhesion. These are my research questions. So, let's go through it. Adhesion is caused by intermolecular forces, like van der Waals and hydrogen bonds, that only occur at the nanoscale. Thus, when you observe two surfaces in close contact, at the microscale, for example, you will see areas that definitely appear to be in contact. However, when you look more closely at the same area, we realize that in fact only parts of it are actually in contact. So, how to measure it and relate it with adhesion? For that, I am using FRET. But what is FRET? FRET stands for Fluorescence Resonance Energy Transfer, and it's a technique capable to quantify the degree of close contact between two surfaces in a distance range of 1 to 20 nanometers. For that, FRET needs two fluorescence molecules named donor and acceptor. And if they are close enough to each other at the nanoscale, a non-radiative energy transfer between them will occur, originating a FRET intensity signal. This signal can be used to determine the FRET efficiency and the exact distance between the donor and acceptor molecules due to the force theory. For example, if I have two molecules, donor and acceptor, at the distance detection range of 10 nanometers, if the molecules are apart for more than 10 nanometers, I will have no signal. And on the contrary, if the molecules are apart from less than 10 nanometers, I will be able to detect a FRET signal. And if the distance is reduced, then I will get a higher FRET signal. For the detection of FRET signals, we used FRET spectroscopy. So, how does this work? First, I need two surfaces labeled with donor and acceptor molecules, as thin films for example, that I can analyze individually and in close contact. Analyzing the donor thin film alone, I will have a fluor spectra in the donor region, and the same for the acceptor alone, in its acceptor region. However, when the surfaces are put together in close contact at the nanoscale, the fluor spectra will look like this, a clear FRET signal, where donor intensity drops and acceptor intensity rises, demonstrating the energy transfer from the donor molecules to the acceptor ones. And from this spectra is then possible to calculate the FRET efficiency of the system. So, putting all together, if I have a donor and acceptor bonded thin films, I will again have the same problem that I explained before. However, in areas with no contact, I will have no signal and therefore no FRET or a significant FRET efficiency. Though, in the areas that are actually in nanoscale contact, I will be able to detect a FRET signal and a high FRET efficiency. In addition to FRET spectroscopy, we can use FRET microscopy. The fluorescence microscope is equipped with a set of filters appropriated for the FRET pair, and the energy transfer signals can be detected using fluorescence images of cross-sections between donor and acceptor interfaces. The images can be analyzed using a sophisticated algorithm from which it is possible to calculate a unidimensional parameter, nFRET, that indicates the average of nanoscale contact between the interfaces. Areas in nanoscale contact demonstrate high N-FRET values, and areas with no nanoscale contact demonstrate low N-FRET values. Therefore, FRET microscopy can also be used for nanoscale contact local analysis. In the overall, if two surfaces in close contact are analyzed by FRET spectroscopy and microscopy and then separated to evaluate adhesion force, a relation between FRET and adhesion can be established because FRET methods can indicate if nanoscale contact is or not occurring, FRET spectroscopy can be used for quantitative analysis, and FRET microscopy can be used for quantitative and local analysis. Do you have any other questions about FRET? In that case, just write me. And if you want to know more about FibreNet, go to www.fibrenet.eu. Here you will find everything about us. Thank you, stay safe, and goodbye.